Hello. Okay, this video is on section 4.1 talking about divisibility and modular arithmetic. Okay, so you all know about division. When one integer, whole number, is divided by another non-zero integer, the result will either be an integer, such as when you divide 20 by 4 and it gives you 5. That's an integer, or not an integer, such as when you divide 23 by 4 and it comes out to 5.75. Okay? Now, if A and B are, here's a definition. If A and B are integers with A not equal to 0, we say that A divides B if there's an integer C such that B equals A times C. Now, in the example we used up above of 20 divided by 4 equals 5, there's an integer, in this case 5, which is like the C here, so that 20 equals 4 times 5. All right, so that's what the reasoning is here. A divides B if there's an integer C such that B equals A times C. So in other words, B is like a multiple of C. I'm sorry. B is a multiple of A if A divides B. Another way to say that, if B divided by A is an integer. Okay? Now, continuing in the definition, when A divides B, we say that A is a factor or a divisor of B, and that B is a multiple of A. Now, we use this notation with a vertical line. The notation A divides B. All right. Now, we write A does not divide B by putting a slash through the vertical line to mean A does not divide B. So here's an example. Does 11 divide 143? Well, yes, if you look at this and play with the numbers, you see that 143 is 11 times 13. So 13 is like the C here. 11 is the A. So it is true that 143 is 11 times 13, so that must mean 143 is a multiple of 11, and so 11 divides 143. Does 7 divide 23? All right. Well, no. Obviously, 7 would divide 21, but when you divide 7 into 23, you get a remainder of 2. You don't get a 0 remainder. So we would say 7 does not divide 23. Okay? Now, an equivalent expression for A divides B uses quantifiers. Remember that backwards E, that it signifies there exists. So there exists a C such that B equals A times C. So that's that same C we had in the last definition. So another way you can say A divides B is there exists a C such that B equals A times C. And we're talking about under the universe or the domain of the integers. Now, let C and D be positive integers. How many positive integers not exceeding C are divisible by D? Okay, well, it's just a whole nother question. C and D are just two numbers. It's not the same C that's in the definition a minute ago. But if you look at the solution, the multiples of D are D, 2 times D, 3 times D, 4 times D. So like if we're talking about multiples of 7, it'd be 7. 2 times 7 or 14. 3 times 7 or 21. All the way up to k times d, where suppose kd is the largest multiple of d that's less than c. Okay, so in other words, let's say c was 69. So we're talking about the multiples of 7, let's say, up until you get to 69, but don't go over that. So 69 is like the c here. But these multiples, there'll be a highest multiple that does not exceed c. Okay, now we write this inequality here that 0 is less than or equal to kd is less than or equal to c. So in other words, kd, that last multiple, is less than or equal to c. Now if we divide all the parts of that inequality by d, you get that k is between 0 and c over d. Now it could equal c over d if d divides c, then it would be a whole number there, but k is in between 0 and c over d. Now we know that k is the largest multiple, so it's actually the largest integer, or we say the integer function, or the floor function of c over d. So k would equal the floor function of c over d. That is the answer to this question of how many positive integers not exceeding c are divisible by d. So, like for example, like the example I was using, how many multiples of 7 are less than 69? Well, you just do the floor function of 69 divided by 7, which is 9. Okay, it's 9 point something, but you round down to 9. So the answer is 9 multiples of 7 that are less than 69. Okay, now here's a theorem, a big 3-part theorem giving some divisibility facts. Theorem 1. Let a, b, and c be integers where a is not 0. Then if a divides b and a divides c, then a divides the sum of b and c. Okay? Now if a divides b, then isn't b a multiple of a? And a divides c, then c is a multiple of a. So what happens when you add 2 multiples of a? Well, you're going to get another multiple of a. I mean, that's one way to describe this, why this works in English sentences. But with math, you want to prove things. So here's a proof of it, and it uses the definition of a divides b and a divides c. So you say, suppose a divides b and a divides c, then there must exist integers j and k. This is like the c in the definition, but we're using c for a different thing here. So there exists integers j and k such that b is equal to a times j, which basically says b is a multiple of a, and c equals a times k. Again, that c is a multiple of a. Therefore, b plus c, well, now we're just using substitution, would be aj plus ak. Now, aj plus ak, I can distribute out an a out of that, and therefore we have that b plus c is a multiple of a because it's a times some integer. Okay? Well, if it's a times some integer, by the definition of divides, then a divides b plus c. All right? So look at that proof. All right, now the corollary at the bottom of the page. If a, b, and c are integers where a divides b and a divides c, then a will divide m times b plus n times c, as long as m and n are integers. Okay? So A is dividing what's called a linear combination of b and c. That mb plus nc is kind of a linear combination of b and c, because you're taking basically a multiple of b added with a multiple of c, and you're adding that up, and that's called a linear combination. But the proof of this is easily done using the second part here first. We know that if A divides B, then A divides B times C. So if A divides B, A will divide MB. And likewise, if A divides C, then A will divide NC. Okay? Well, then you use the first part that says if A divides two things, then then A will divide the sum of them. And so you add the two parts up and you get the corollary. All right, so the division algorithm is an important algorithm for some things we're going to be doing later. Now, it's not really an algorithm, although it has that traditional name. It really is a theorem defining what a quotient, a divisor, and a remainder are in a real precise way. So Theorem 2 is called the division algorithm, and this is what it says. Let A be an integer and D a positive integer. So D is the divisor, the thing you're dividing by, and it has to be positive in this algorithm. Okay? Let A be some integer. That could be positive or negative. So that's what we're dividing into. D is the positive integer that we're dividing by. Then there are unique integers Q, the quotient, and R, the remainder. With R, now this is important, R has to be between 0, including 0, and D, the divisor. It has to be actually less than D. So it's between 0 and 1 less than D. That's what the remainder has to be. Such that, and this is a key equation, A equals D times the quotient, Q, plus R. Okay? Now, for example, let's say we're dividing, thinking about dividing 23 by 5. Okay? So 23 is the A. Thing we're dividing by, D, is 5. Okay? Now, you know that the remainder, when you divide 23 by 5, is 3, and the quotient is 4. So it should work in this equation that 23 equals 5 times 4, because the quotient was 4, plus the remainder, which is 3. And it does, because 5 times 4 is 20, plus the remainder is 3, which gives you the original 23 number that you're dividing. So now you can't use D times 3 plus a remainder of 8. Like, for example, 5 times 3, which is 15, plus 8. Although 15 plus 8 is 23, you can't use a remainder of 8 because R is not between 0 and the divisor. Okay? Your remainder has to be a positive number between 0 and the divisor. Okay? Now, in this situation, A is called the dividend, the number being divided. D is the divisor. Q is the quotient, which has to be an integer. And we have this notation for how to find the quotient. Now, this comes from computer languages. Q equals A divided by D, but it only yields the quotient. It doesn't give the remainder in that case. The remainder is given using the mod command, because you know modular arithmetic, it's all about the remainder. We just looked at that. So take a number and divide by d. I'm sorry, a mod d means we're finding the remainder. A div d means we're finding the quotient, okay, in these computer-like commands. So let's look at some examples. First, look at this note. For integers a and d, with d being positive, we have a div d it's the floor function of a divided by d. All right, that will give the quotient, which is a div d. So the floor function of a divided by d. So for example, if a was 23 and d was 5, 23 divided by 5 gives you 4 point something, and so you round that down, it would be 4. So it gives the quotient. And then a mod d, this is the remainder. So you take the original number, in this case 23, and subtract d times that quotient. Well, d was 5 times the quotient, which was 4. That would be 20. And so you go 23 minus 20, which would be 3. Okay, so in the case of a being 23, you get the remainder of 3. That's just like in this next example, and you realize it was so close to it, but a is 13 and d is 5. So 13 divided by 5, that is really the quotient only, not the remainder, because div gives the quotient. But the floor function for 13 over 5 would be the floor function for 2.6, which is 2. Right? That's because 5 goes into 13 2 times, of course, with a remainder of 3. And that's what the next thing figures out. 13 mod 5 is the remainder. So it'd be 13 minus 5 times 2, okay, because the floor function of 13/5 is 2. So 13 minus 5 times 2 is 13 minus 10, or 3. So the remainder is 3, as you knew. Okay. Next question, what are the quotient and the remainder when negative 47 is divided by 7? Now this one is kind of a strange question, because the number a is actually a negative number, okay? But what's weird about this is you can't think of it as just positive 47 divided by 7, which of course would be 6 point something. So the quotient is not going to be 6. It's actually going to be, actually not going to be negative 6, it's going to be negative 7. And here's the reason why. All right, so the solution says negative 47 is 7 times negative 7 plus positive 2. So we're going to use the negative 7 for the quotient, and the remainder being 2, since we had to have the remainder be a positive number between 0 and 7. Okay, if we had tried to use negative 6, then you'd have negative 47 equals 7 times negative 6, which is negative 42, which means you'd have to use a negative remainder. And it violates the division algorithm to have the remainder be negative. It has to be between 0 and the divisor, in this case between 0 and 7. So we had to use negative 7 for the quotient so that we could have a positive remainder. Okay? So you sometimes have to go further to the negative side so that your remainder is then positive. So you'll have some questions on the homework like that. Now, modular arithmetic is related to this. It's used when you only care about the remainder when numbers are divided by the divisor. Okay? So, if a and b are integers and m is a positive integer, so now m is kind of what you're dividing by. So m is what you're dividing by. Then we say that a is congruent to b modulo m if m divides a minus b. Now this takes a little bit of getting used to. Let's talk about it some more. In symbols, this is when m divides a minus b. Okay, so we use that vertical line for divides. Now, we denote it congruent using the triple equal sign, three-line equal sign. So A is congruent to B mod M, and say this is a congruence using the modulus M. But essentially this happens when A and B have the same remainder when they're divided by M. Okay, so that's basically it, when they have the same remainder. All right, let me give an example. 6 and 11 divided by 5. Each of them divided by 5. Okay, now 6 and 11. What's the remainder when you divide 6 by 5? It's 1, right? What's the remainder when you divide 11 by 5? It's also 1, okay? Now, what happens when you subtract 11 minus 6? You get 5, and 5 is divisible by that difference 5. I'm sorry, the difference 5 is divisible by the number 5. Okay, so that's really, what we're saying. So 6 and 11 would both be congruent modulo 5. All right, let's look at some other examples. Is 11 congruent to 2 modulo 3? Is 11 congruent to 2 mod 3? Well, since 3 divides the difference, 11 minus 2, then yes. Okay? Now, 11 minus 2 is 9, and 3 divides 9. So then 11 is congruent to 2 mod 3. Now, up here in italics, I had said essentially this happens when A and B have the same remainder when they're divided by M. What's the remainder when you divide 11 by 3? Well, 3 goes into 11 3 times with a remainder of 2. Isn't 2 the remainder when you divide 2 by 3? It goes into it 0 times with a remainder of 2. So both 11 and 2 have a remainder of 2 when you divide them by 3. Okay, here's another example. Are 43 and 63 congruent modulo 7? Okay, well, when we find the difference of them, 63 minus 43, we get 20. But 7 does not divide into 20, the difference. So 43 is not congruent to 63 mod 7. All right, so the quick, easy test is if the mod, which is 7 here, divides into the difference of the two numbers. Now, you can also think of it as, do they both have the same remainder when you divide them by 7? What is 43? What's the remainder when you divide 43 by 7? It's just 1, right? Okay. Now, what's the remainder when you divide 63 by 7? It's 0, because 63 is a multiple of 7, right? 7 times 9. So they don't have the same remainder when you divide by 7, so they are not congruent, mod 7. Okay. Some additional theorems. Theorem 4, Let m be a positive integer. The integers a and b are congruent modulo m if and only if there's an integer k such that a equals b plus k times the mod m. So why is that? Well, if you add a multiple of the number you're dividing by, won't the remainder, when you divide by that original number, be the same as the remainder after you add the multiple? So that's really the reason for it. Now, there's a proof on page 241, but another way to think of it is if you can see that a congruent to b mod m, okay, and that's what the first part of this statement says. The integers a and b are congruent modulo m, so we're just writing it in symbols here. You know that a congruent to b mod m means that m divides the difference, a minus b, just like we discussed earlier. Now, if it divides the difference, then if you do a little algebra to this last equation in the theorem, you move the b to the other side, you subtract b from both sides, you get km equals a minus b, or the two sides switched around, you get that. Km equals a minus b. Well, of course, if m divides the left side, then m is going to divide the right side. And so that's essentially the same as saying m divides a minus b. But you can look at the proof on 241 and study that. Theorem 5, let m be a positive integer if a is congruent to b mod m and c is congruent to d mod m, then a plus c will be congruent to b plus d. Okay? So in other words, if you have a congruence here and another congruence, if you add the left sides and add the right sides, it's still congruent. Now, the next part of the theorem says a times c will be congruent to b times d. This says that you can multiply the left sides of the two congruences, and that will be congruent to the right sides multiplied together. Okay? Now, it works going one direction only. If you know a congruent to b mod m and c congruent to d mod m, then you could add the left sides together and the right sides together, and it's still a congruence. Or you can multiply the left sides and the right sides together, and it's still a congruence. But you can't start with them added together and then split them apart into separate congruences. Okay? It doesn't go the other direction. So the converse is not necessarily true. All right? Now, if 13 is congruent to 8 mod 5, which it is because the remainder when you divide 13 by 5 is 3, and the remainder when you divide 8 by 5 is also 3. So they're congruent mod 5. And 6 is congruent to 21 mod 5. Then I could add the left sides, 13 plus 6, and that's congruent to the sum of the right sides, 8 plus 21. Okay, which if you add that up, you get 19 is congruent to 29. Now, what is the remainder when both the left side and the right side of that congruence are divided by 5? Well, it's a remainder of 4 on the left side and a remainder of 4 on the right side. So, of course, they're congruent mod 5. All right? Now, you can also multiply the left side. So 13 times 6 is congruent to 8 times 21, which if you multiply that, you get 78 congruent to 168. Both of them are congruent to 3 mod 5 because the remainder is 3 when you divide by 5. Okay, so this is something to get kind of used to, all this thinking, but once you do get used to it, it comes a little bit easier. All right. Now, mathematicians have been using what's called arithmetic modulo M, or modular arithmetic, for quite some time, a couple centuries at least. But we're going to be studying it in regards to computers because modern security systems, including the RSA crypto system, we're going to talk about cryptology in a couple sections here, is based on modular arithmetic. Okay, and we'll be looking at some of that. But let's get the basics of this modular arithmetic first of all. So what this is, it's doing operations on a subset of the integers, of the positive integers, and it's ZM. Now ZM is the set of integers from 0 all the way up to m minus 1. Okay, so if your mod is 7, it would be arithmetic involving just the integers 0, 1, 2, 3, 4, 5, 6, all the way up to one less than whatever the mod is. Okay, if you're operating in mod 29, then it would be 0, 1, 2, 3, 4, all the way up to 28. All right, so those are the only integers that are allowed in this type of arithmetic. Whatever, you know, from 0 all the way up to whatever one less than the mod is. Now, we use this symbol that's in red here, plus, and we put the mod right kind of as a subscript to indicate we're doing modular arithmetic. And what we're doing is adding a plus b, but figuring out what the mod m is, in other words, the remainder. We're doing a plus b and then figuring out what the remainder is in mod m, whatever m is. And then a times b, it's using a mod, and again we're using we're discussing the remainder when you take a times b and divide it by m. Okay, so for example, here's 12 plus, using mod 9, 15. Well, add 12 and 15, you get 27. And then if you divide 27 by 9, what's the remainder? Well, the remainder is 0. So 12 plus 15, using mod 9 arithmetic, is 0. Did you know 12 plus 15 is 0? Well, in mod 9, it is. 6 times 4 in mod 9, well, 24 mod 9. Well, what's the remainder when you divide 24 by 9? Well, it goes into it 2 times, leaving 18, but from 18 to 24, it's an additional 6, so the remainder is 6 for 24 mod 9. So 6 is the answer to this. So 6 times 4 in mod 9 is 6. All right, now many of the same properties are satisfied in modular arithmetic as in ordinary arithmetic, such as closure, associativity, commutativity, identity elements. Identity elements would mean you add, what number do you add to another number and so that other number is not changed? Well, 0, right? So 0 is the identity element for addition. What number do you multiply another number by so that other number is not changed? Well, 1, right? Multiply, so 1 is identity number. So modular arithmetic has these identity elements as well. Additive inverses, fine. You can add a positive and a negative and you get 0 in modular arithmetic. And distributive property. distributivity. But there is no multiplicative inverse property, okay, for modulo arithmetic. However, since we're working in M, so we only have integers, not like fractions. So multiplicative inverse is like the reciprocal, okay? All right, so that's the lesson on divisibility and modular arithmetic. Hopefully doing the homework will help you to get acclimated and used to this notation and these concepts. All right.